Shall we? So we are starting electric potential. Now, there are some, this has to be understood very conceptually, okay? So, first of all, we'll understand the concept of something called work versus potential energy. Work versus potential energy. Let us understand this concept with some analogies. Then we will come to electricity, discussion of about electricity. So let me think about a setup. Right, I have got a setup here. Right, and this setup is all about a spring system. Let's say there is a spring, and the spring right now is not extended. The spring right now is not extended, and I have a body that is attached to this spring out here. Okay, this is a body, and the spring is not extended. All right, and say suppose right, spring is not extended, and there is a body that is attached to this spring. Fair enough, no issues. Okay, now what you try to do is that you try to compress this spring with this body attached. What I mean to say is that, say suppose I have compressed this spring, and after compression my body is now at this position. Okay, this is the position of the body. This is the position of the body. Say this is my body, and I have compressed the spring. So right, I have compressed this. How much distance did I actually move in actually compressing the spring? So you will agree with me that I have moved this much distance to compress this spring. This is the distance. Let's say this distance is some distance x. Right? How did you compress this spring? You compressed this spring because you applied something which is known as the external force. Understood? And you apply this external force and you have compressed this spring. Don't you think that once you compress the spring also has a spring force, right? The spring also has a spring force, and that force is actually in this side. It's the spring force, which is given by, always given as negative kx, because the spring force, work done by the spring force is negative k. This is the work done. So let me not write this. I'm saying I have a spring force which is actually in this direction, fs. Understood? Now try to think, you took this object and you have compressed it and you have kept it here. What happens if you remove that external force? This body will fly away. So don't you think that you have energized the body? Okay, there is some potential energy at this point. Let's say we call this point at A, and we represent this potential energy by UA. There is some potential energy out here, right? Once you try to compress it, did you increase its potential energy or you reduced its potential energy? Increase this potential energy, and you have brought it to a position B, and here the potential energy is UB, right? What I will be interested with, how this chapter goes, I have nothing to do what is the potential energy here. I have nothing to do what is the potential energy here. Think that I am a tutor, I am a teacher, I am a laborer. Then what should you pay me for? The service that I have given you. And what is the service? Isn't the service the difference of the potential energy between these two? What you were is nothing of my botheration. What you became is nothing of my botheration. How much addition or subtraction happened to you is what I should be charging as money from you. Whether I'm a laborer, I'm a painter, I'm a tutor or anything. Don't you agree? If I'm giving a tangible service which you can measure. So in this whole process, there is a change in potential energy delta U, which is given as final potential energy minus. Now the final potential energy is UB minus the initial potential energy is UA. Do you agree? And if I see it from the perspective of this external force, then where did this potential energy come from? The question arises, energy cannot be created nor be destroyed. Don't you think I sweated myself to push this spring here? I've done some work on it. What is work done? Force into displacement. I have moved it this much distance. The displacement is in this direction. The force is in this direction. Do you agree? Therefore, I can just write that the external work that I have done is equal to the external force multiplied by the distance that I have moved. Agreed? As I start compressing the spring, immediately the spring force also starts to develop. Spring force also starts to develop. Now, I am not compressing it very fast. I am not compressing it slow. I am not overpowering the spring. I am just applying force which is sufficient equal to the opposing force. Do you agree? I am just giving a force which is sufficient to the opposing force. That means the opposing force is actually acting in this direction, the spring force. If you see the work from the spring force perspective, then the force is in this direction, the displacement is in this direction. The angle, what is work done? Fs cos theta. If you have forgotten, work is the dot product of displacement and force. Then it becomes Fs cos 180. So the spring force work will become what? It will be becoming the work as the negative work, if this is right. So if I say that the work is this, I can also say that the external force work is equal to the negative of the spring force multiplied by the distance x. Do you agree with me or not? You agree with me? Right. And then try to analyze another scenario. So once you compress it from here to here, you have built up what? Your work. What is the unit of work? Joule. Entire work has been built up into potential energy. System is now energized. And you release it. Once you release it, the potential energy, whatever this is the difference of potential energy, right? The delta U, which is equal to the UB minus UA. This is the potential energy built up. This potential energy was nothing, but it was the external work that was done on this system. What was the external work done? The work done in moving the charge from where? Moving the charge from A to B. See the notations. Work done from moving A to B. External work done. And if I see this work from the electric force, the spring force perspective, I will say negative of this work. Is this negative understood? Okay. So this work got converted into the potential energy. And now I have released this block. What do you expect the block to? The block will fly out. Motion will come in. That means this delta U will be slowly coming down, and there will be a kinetic energy which will start to pick up. You can call that as delta kinetic energy also. Here the velocity is 0, and here there will be some maximum velocity. Right? One perspective we need to understand here in physics is that you don't measure anything accurately. All you measure is difference. What is your age? 17 years. Your age difference is 17. Because it was presumed that the day you were born is 0. And what is your current age? 17 years have elapsed by. 17 minus the date initial age is 0. You think that the potential energy of the mouse when kept on the table is 0. But there is a height as compared to the ground. But you are right now seeing the experiment from the ground as the table. Potential energy 0. I now raise it here, potential energy mgh. So what is this is not the potential energy here. It is the difference of potential energy at this level and this level. Because if you see from the floor, then this has some potential energy. If you start making a drill, if you cut out this portion, won't the mouse fall down? The mouse will fall down. Means it is energized. So we say that the potential energy will be coming down and the kinetic energy will be picking up. In a sense that all delta U will be spent to create another delta KE, which means that the total energy is ultimately conserved. My hard work, muscular work, created potential energy in the spring system. The spring system released it and created kinetic energy. Such sort of a work done is this is known as a conservative work. Conservative work. And conservative works are actually done by conservative forces. Conservative forces. Do you understand? Our example was with the spring. So the spring force is a conservative force. The spring force is a conservative force. And conservative work depends only on final and initial position. It does not depend which path you took. Which path you took. It depends only on final and initial. Which path may not be clear with this example. Still, I'll give a try. If you would have taken up this spring little bit on top, whatever you have done, and stay again brought it compressed somewhere here, the potential energy in this spring potential, we call it as elastic potential energy. There are two types of potential energy: gravitational potential energy and elastic. Elastic is by constraint. Catapult has been pulled, elastic. If you could have brought this point of the spring here, no matter how you have brought it, the potential energy will be the same. That's what we mean by this. It depends on the final and the initial position. It does not depend on the path taken. Is this first example analogy understood by you? Right. This is what you will be studying now slowly into your electrostatics also. Let's see another example. Okay, let's see another example. Let's take our example number 2. Our example number 2 is, I'm on planet Earth, right? I'm on planet Earth. Planet Earth has got a property that every object is pulled towards the center of the Earth. Do you agree? Right? Now I am doing a different activity. What is the activity I am trying to do? My activity is that there is a small mass on the surface of the Earth. Do you think that this mass is being attracted to the center of the Earth? Yes, obviously, that's why we are standing. Otherwise, this mass should have flown away, like in Moon and other planets. Agreed, right? So now what I'm doing, I'm trying to move this mass away from the surface of the Earth. Okay, I'm trying to move it away from the surface of the Earth, and I take the mass out here. Right. This mass definitely has a weight which is given by the mass multiplied by the acceleration due to gravity. And I start lifting it with a force which is just equal to its weight. This is my lifting force, which is equal to the weight. And I start lifting it, and I lift it by a height h. So how much work did I do? My force multiplied by h. And my force is what? mg. So I create an energy, and if I say that this was my UA, and I take this as 0, suppose this is 0, assumed, then I take it to a position UB, and at UB, the potential energy is mgh. Is the body energized? Yes, the body is energized, because allowed to release, the body will flow. Are you understanding? And the delta U in this process is actually the work done by me, the external work done by me, which is equal to WB minus WA. The two forces, if I see from my manual force, I am doing a positive work because the force is on this side. Whereas if you see from the gravitational force, it is trying to pull in this side, displacement is happening on the other side. The gravitational force is doing a negative work. Is this concept understood once again? Okay, fine. So my question comes here once again, that earlier we were doing an electric force. So all the, if you release here, if you release it, then all the delta U's will again convert to all the delta KE. This is also conservative work. Conservative work. That means the force is the gravitational force. And the gravitational force is also a conservative force. It depends upon the initial and final position. Once again, conservative work, it does not depend upon which path you took. Sir, I am still not able to understand. Can you elaborate it more? Well, let's try to elaborate it more. Okay, let's see. Right? The person was here. The person took the steps. The person has a weight, right? He has a weight, mg. The person took the steps, and the person reached B spot, right? When the person reached B spot, then again we see that how much of a height did the person actually gain? The person gained a height of h. His potential energy at this stage is mgh. How did he go? By the stairs. In potential energy, it doesn't matter how you went. Only the initial and the final position. If he was also taken by a rope also, if I would have pulled him by his hair in this manner and taken him up, then also the potential energy. Because if you drop him from here to here, the energies that he will spend will be the same. Have you understood? That means that if you have a planet, if I have a planet, say this is Earth, then there is some region around Earth. Okay, there is some region around Earth, and let me say there is a region, sorry, there is a region around Earth where you feel the gravitational field of the Earth. Every object in this region will be pulled near it. Are you understanding? This is the region of the this is the region of the gravitational field. Gravitational. Children, it is not bound by a specific boundary. The gravitational field is infinity. The more and more near you are, the more and more you will be getting into more field of it. In this gravitational field, if there is any object, that object is actually attracted by the Earth. This is our understanding. If you try to move it away from this force, you are actually creating what? You are energizing the system, because every time you pull it away, more and more energy will be imparted. And your pulling away won't be that easy. It will be difficult. Like if you try to pull a heavy object from the ground, you are also doing enough amount of work. Your energy then gets stored into it. I hope now this story is understood. Okay. Whereas if you see the gravitational force or the force of attraction, these all are actually G m1 m2 upon r square. So what we understand, this force is attributed to the product of the two masses, this being a constant, follows the inverse square law. Clear? So what all did we understand? Whatever is the change in potential energy, children, we are least bothered about what is the potential energy. We are only bothered about, if you have slight bit of still rejection to understand it, let's suppose the potential energy UA, it was UA plus some value alpha, and here also it is UB. If you add an alpha here also, how does it matter? Because you're all going to find is UB minus UA, that is the delta U that you perform. So the external work gets added. If this external work is viewed from the internal force, then it becomes negative. Okay, and when it viewed from the external force, it's a positive work done. Is this much clear or not? But this was all mechanics. We are supposed to study electric potential. So let's go around electric potential. Now say I bring about a charge out here. This is a positive charge. Okay, I have a positive charge, and this positive charge is Q, and so made that I bring Q at no other place, but just for our understanding, I am keeping Q right at the origin of a Cartesian coordinate system. I am keeping Q at the origin of a Cartesian coordinate system, so that it becomes easy for you to understand, right? And Q is a positive charge. If Q is a positive charge, then the Q has an electric field in and around it. What is the direction of the electric field? Radially outwards, right? And then I am bringing another test charge. And this test charge is brought in its vicinity. The test charge is like that wooden block which I was loading on that spring. Okay, the test charge is brought into the vicinity with some considerations. Number one, I am taking the test charge as positive, is greater than 0. Okay, the next one I'm saying it is infinitesimally small. The main idea behind this infinitesimally small is that it should not hamper Q's position. Why it is because if the charge was bigger, maybe Q would have got repelled. It should not hamper Q's position or its electric field. Means it is a charge, but once it enters your arena, it does not create any disturbance to you. Is this understood? Wherever I introduce this charge, children, I introduce this charge out here as Q, right? So let me make it with a different color. So So I introduce this charge, say here, and I call this charge as Q. So there will be a shortest straight line which will be joining these two charges based on our Coulomb's law of funda. This is shortest straight line which is right. Now, what is your analogy about the electric field? My electric field will always be in this direction. This is the direction of the electric field because it is a positive charge, right? As a result of this, the charge is going to face an electric force. There will be an F electric force, and the F electric will also be in this direction because it is in the direction of the electric field. And how do you define the electric field? Force upon F divided by Q. So this should be nothing but in vector form, the Q multiplied by the E. Is this much understood or not? It is facing in, right? And let's say we have kept this charge at a position A. Now some more consideration. Say from A, we move the charge to a point B, and I now move the charge to a point B. So children, this is my point B, right? This is my point B. Your book, if you read, would have been cleared, but just because that spring diagram and this was not clear, now everything will get cleared. We move the charge with B very, very slowly. Why are you moving it very, very slowly? So that acceleration is zero. Acceleration is zero. And you apply a force, you apply your external force whose magnitude is just equal to the electric force. Means in vector form, if I write it, I can write the external force is negative of the electric force. Children, is this much understood? Right? So what are you doing? You are giving an external force to it, right? So you are giving an external force to it. This is your F external, the external. So let's see the concept once again. I have brought a charge. The charge is Q, and I'm moving this charge from A to B. Am I not doing something like the spring wala experiment? Some force is trying to push me out. I am trying to push this object inside against that force. Don't you think that I will be energizing this body? Okay. So whatever be the position, there is some energy, potential energy associated here. Everywhere there will be a potential energy because charge cannot stay here. The charge will always move out from this position because you are introducing the charge where the only difference between this and the gravitational field was in gravity it would have moved this side. If you keep a charge here, the charge should always move this side. Now you will say, no sir, I have kept it very far away. Why are you keeping it far away? Keep it a little bit nearby so that the impact can be felt. And you are right now operating within the electrical field of this particular charge Q. Okay, this is our big charge Q. You are right now operating in the electrical vicinity. So if you would have kept a charge here also, then also it will have some energy. It's energized, and you're trying to move it. As you start moving it, then what happens, children? You are doing some external force. Okay, so you are doing an external work, W external. And let's say we start moving it in very slow distances or slow displacements. So can I write this as the external work? Now, when I'm moving it very slow, I will not like to approach it in directly like this. I would say I'm doing some very small external works which are equal to the small external force which is constant multiplied by the small distances dr that I'm moving in this side. Right? In the language of work, I can say that it is not dr. I'm moving in this side. Is this understood? This is also a vector quantity. This is also a vector quantity. Okay. For more simplicity, we can also add one more item out here. We can say that the distance from here to here, say the distance from here to here is given by a vector, and that vector is the r vector, right? R vector. And you're moving in this direction slowly. Your movement is opposite to the r vector. You're moving dr small distances. So you're moving from A to B, children. You're moving from A to B. Let's not draw this R here. It will confuse you. Let's take it out. Okay, we are moving small distances, say R, or you can say X also. Let's keep this X. If you get confused, so let's keep this X. Okay, not some dx distances that we are moving from here. Why we don't write X? Because since you have already shown it as X and Y, it doesn't make any sense that this will be X. That's the reason we put R. I hope you are not having any confusion to understand this. Is this okay to understand for dr, right? Correct, you're moving some dr distance across it. Now if I see this external work, then I would also write that I would put a negative with the external if I use the electric force and I use the same concept. Is this understood? So the work done by electric work done is opposite of the external work done. As a result, now if you see the work external, the complete external work, this is the work done from moving from A to B. Understood? This work is analogous to the increment in the potential energy in the system, which can be given by delta U, which is given by potential energy UB minus UA. Have you understood this much or not? Is this clear? This is called the electric potential energy of the system, the electric potential energy change. So what is the change in the electric potential energy? As a charge moves from one position to another, we are actually incrementing the system. We are incrementing the system with an additional potential energy of delta U, which is given us the difference of the final potential energy minus the initial potential energy. But this equation holds. You had some very basic assumptions right at the start. You said that you are taking what? You are taking a positive charge and you are moving this side, right? Just imagine if we would have taken, now say we are trying to draw something called a slab. Charges are like, right? Charges are like means your test charge versus source charge. The two charges are like in this case, and we have taken both as positive. What is your comment on the delta U of the system? The delta U of the systems becomes positive. The potential energy of the system increases, right? Fine. If you take unlike charges, if I'm taking unlike charges, then just try to see what happens in unlike charges. In unlike charges, the electric field will be on this side. Electric force is on this side. So the electric force wants to pull it this way. You are also pushing it this way. Are you energizing the system? No, not at all. If it is unlike charges, then the delta U becomes negative. The potential energy of the system comes down. You are lowering the person. How are you charging the system? You are actually reducing the charge of the system. This is also one concept you should understand. Right? Delta U. Charges are alike, then the potential energy increases. If the charges are different, then the potential energy reduces. Is this clear so far? So, the external work done can be written as the integral of the external force into the small drs, okay? And where will you integrate it? I will integrate it from A to the point B. Clear? Similarly, I can also say that the external work done should be equal to integrating from A to B, but if I use the electric force, then it becomes this into dr. Same concept. From the perspective of the electric force, it's a negative work. From the perspective of the external force, it's a... So, are we in a position to now define What is electric potential energy change? The electric potential energy change is defined as the external work done in moving a infinitesimally small charge, what we call it test charge, from a point A to B. So to make it more better definition, what is the electric potential energy difference between 2 points? The electric potential energy difference between 2 points is equal to the external work performed in moving a unit positive charge or a test charge. A test charge is always a positive charge. Don't say unit, just say a test charge. Just say a test charge. It can, but the test charge is taken such that it is positive and extends more. If you want to be very elaborate, very slowly, without any acceleration, from one point to another, encountering the electric field of that source charge, or encountering the electric field of that space. So let's get it more clear. Don't worry at all. They are asking that given a space, what is the electric potential energy difference between 2 points A and B, given a space? So let's understand the definition. The electric potential energy difference between A and B, where A is taken as the initial and B is taken as the final. That means I am assuming that I am trying to define a delta U, which is a UB minus UA, because this is my final position and this is my initial position. Okay, it's always initial minus final. So the electric potential energy difference between 2 points in space, the points being referred as A and B, A being the initial point and B being the final point, is defined as the external work done to move a test charge, and the test charge is moved such a way that the test charge is greater than 0. The test charge is very, very small. This is another. We don't write all this, but these all are actually important in the definition. And Q moves with an acceleration which is equal to 0. Right? Encountering the electric field of this space, this field should have this space should have an electric field. Our electric field was created by a source charge. At that moment, the external work that you do to move this charge from here to here, how? With a very small charge, positive charge, no acceleration, from here to here, whatever work you have done is defined as the electric potential energy change between these 2 points. And this can be written as how much? We will write this as UBA, which is equal to UB minus UA. Or you can write it as UAB. UAB is the correct word, final minus initial. So we will write it as UAB, which is equal to UB minus UA. Tell me, children, have you understood this much or not? This is called the electric potential energy difference between 2 points. And this is the very basic. How do I put it analogous to your daily life? In your daily life, you are every day habituated to ask me, sir, what is your age? What is your age? As a physics student, you should ask me, sir, what is your age difference between 2 points in your life? One is the current point, and one is the point the day you were born. But you are always asking, what is your age? Means, what are you referring? The age at the current point. So for that, we need to first understand what is the age difference. There was never a current point age, beta, because my current point is going on changing. There is an age difference you are measuring. But in daily language, you don't every day say, sir, when were you born and what is the day to day? You are more interested to know what is current age. Similarly, here also, now since you have understood the concept of potential energy difference, you would be also interested to understand what is potential energy at a point. Because in mechanics, you are habituated to know that if you lift a body through a height h, the potential energy is mgh. What? At this point, the potential energy is mgh. This is what physics has taught us. Not exactly. The difference of potential energy between here and here is mgh. But this one you never consider. But right now, all different study that we did, we considered this also, this also. That's why you got delta U. But you as a student would like to know sir, what is the potential energy at B? Understood? So from electric potential energy difference to you are coming to a concept now which is called the electric potential at a point. Electric potential, right? And electric potential means electric potential energy. Please understand the three concepts you will study. The first concept was electric potential energy change or electric potential energy difference. First, what did we study? All these was delta U. Delta U was given by UB minus UA. You start thinking this as 2026, and this is the date in which I was born. So you are measuring my age difference. But every time you talk with me, you just want to know this one only. This was delta U, delta age. This was delta age. Now I will try to know what? Age. I will try to know age. So I will be interested in what? I'll be interested in only the 2026 data. 2026 data. That means I want to know what is the potential energy of a system, right? U. And to know U, 2026 data, you were very smart. What you did, you said that at 1977, the age was 0. So you saw how many years have left and you took out 0. And then you say that my age today is 48 years or 46, 47, 9 years, whatever it is, you are putting it out here. I now want to know what is the potential energy here. I knew the difference. That means I have to create a 0. Otherwise, you cannot get a perfect figure. You have to create a 0. Some datum is required. So that 0 creation is a very interesting concept. Just like if you add some potential energy here and here, it does not cause any difference to the age difference. But I now want this age. When you wanted this age, you created my age at 77 equal to 0. Is there any way in this analogy that I can make UA equal to 0? Because if UA is made as 0, then my delta U just becomes U, which is equal to UB minus UA, and finally it is just UB. And I say that is the potential at B. This is the approach I want to have. How do I make this UA 0? In order to make UA 0, we need to move our charge and consider another point here where all these engineers, mathematicians and physicists said that this is a point infinity, and at infinity any potential associated with it is 0, because neither you have seen nor I have seen. And the potential is actually felt. Why do you feel this potential energy? This potential energy is all felt because of this thing. Just see, where is it? Where were we? This potential energy is all felt because of, was this the first slide? Yeah, I had wrote it. Where is it gone? Where is it gone? Yeah, because of this QE. And what is the definition of E? KQ by R square. KQ by R square. If you are moving far, far away, the electric field itself vanishes. If the electric field vanishes, the force also vanishes. If the force vanishes, no work can be done. So if no work can be done, then we can assume that your potential is almost 0. So the concept now we say is that delta U is equal to UB minus U infinity, which is equal to UB minus 0. And now this delta becomes nothing but the potential energy. The potential energy, so now you need to define, see, go back by the definition. The first definition was, what is the electric potential energy difference between 2 points? Electric potential energy difference between 2 points is the external work done in moving a test charge from one point to the other. Obviously, taking care of some conditions, test charge should be positive, test charge should be moved infinitesimally small, test charge should not have any acceleration, test charge should not hamper the electric field out here. That we don't write all these things. What is the electric potential energy of a point? The electric potential energy of a point in space is defined as the external work done in moving a unit positive test charge from infinity to that point. Have we understood the second definition? So in this, we are bothered about the external work done, and this external work done is W infinity to B. That means the charge is being moved from infinity to B. So, and you are doing what? You are doing W infinity B in this process. This W infinity B is actually the difference of the potential UB minus U infinity, which is equal to UB minus 0, which is equal to UB, which is the electric potential energy at B. Electric potential energy at B. Understood this concept? Grade 10, you started with only this. What is electric potential energy at a point? What is electric potential energy between 2 points? The electric potential energy between 2 points, or the difference of electric potential energy between 2 points, is defined as the external work done in moving a test charge between the 2 points, with some considerations which you already know. And with that, what you get is known as the electric potential energy difference. And if the initial point, instead of being any arbitrary point, was infinity, then you are actually measuring the electric potential of this point. Not electric potential, the electric potential energy of this point. Our next concept comes to understand something which is known as electric. Our next point would be to understand a concept which is known as the electric potential between 2 points, and thereafter we will try to find out what is the electric potential at a point. There is absolutely no need to get confused. Your study was 2 points, A and B. First, you measured what was delta U. This is electric potential energy difference. Then you measured, then you did infinity, you measured UB. This is electric potential energy. This is EPE difference. Have you understood? Now we will have again 2 points, A and B. We will try to measure what is known as electric potential. Just the potential, not the potential energy. Potential. How much potential does this child has? She can work wonders. How much potential does this samosa shop has? Huge potential. He can pull a person from Secunderabad every Sunday to have samosa at his shop. That means his potential is very high. Right? So let's try to divide that. So when we are talking about between these 2 points, you actually see that you created a delta U in the format of UB minus UA, which you said was the external work that you tried to do from moving from A to B. This external work you did for whom? For whom did you do this external work? Tell me. For a test charge. For a test charge. You did it for a test charge. Right? You also know a relation that the electric force on the test charge is given by QE. That means more stronger is the electric field, your test charge is always positive, more you have to sweat out, because the electric force will be more stronger. So more spring is very tight, you have to move it very, very fast. Right? Can we abolish Q from here and just talk in terms of the E? Because it depends. The heavier Q you bring, the more work you have to do, the more force you have to apply. Imagine the spring is tight, plus you have brought a heavier block. Isn't the pushing much more difficult? You were so far moving with a small block. Let us move away with these blocks. Now, block is to your choice. He may bring a small block, you may bring a heavy block. What you and he will both will encounter is that you cannot escape from this E. The E is same. The spring is the same. So why are you getting, mind is diverted between 2 variables? Let's keep 1 variable, right? So how much is the per unit sweat he gave? Divide his work by his weight. Divide your work by your weight. Divide his work by his charge. Divide your work by your charge. Now the value that you are getting is per unit charge. Don't you think it should be same? It should be same. Are you understanding? You're trying to measure the gravitational pull of the earth. What is the gravitational pull of the earth? mg. That is called the gravitational field. He has brought Superman and he's trying to see how Superman is attracted. You brought grasshopper. Let him divide his mg by Superman's m. You divide your mg by grasshopper's m. Both of you will come down with g only, na? Which is the gravitation potential of the earth at that particular spot. So we define the electric potential as there will be a potential energy difference. Now we are seeing what is the potential difference. The potential difference is noted by delta V. This is known as the potential difference. Imagine in class 10 you used to talk a lot PD, potential difference, PD. Now since you have used the word delta V, that is potential difference, there should be at least 2 points. Do you agree or not? 2 points must be there, otherwise how can you create difference? Sir, the 2 points are the same 2 points. The 2 points are the same 2 points. VB minus VA. What is VB? Potential at B. What is VA? Potential at A. Sir, what is this? The external work done from A to B divided by the charge that you brought. Understood? So now again definition changes. So finally we can also say the potential difference is the external work that you did from A to B divided by Q. Right? Same thing. So see, what did you define here, children? Look here now. Electric potential energy difference between 2 points is the measure of the external work done in moving a test charge from one point to the other. Electric potential difference. Now you are trying to find out electric potential difference. So what are you measuring? You are measuring VB and VA. You are trying to measure delta V, which is VB minus VA. This is equal to what? This is equal to the external work done per unit charge that is being moved from A to B. Per unit charge. Per unit charge. Is this clear? Per unit charge. And this is VBVA. W external is also what, beta? Delta U by Q. Delta U by Q. Delta U by Q is also UB by Q minus UA by Q. Nobody stops me. Right? Got it? So what is the electric potential difference between 2 points? The electric potential difference between 2 points is the work done per unit charge. Per unit charge. Per unit charge. Whatever you have brought. Our next consideration would be to find out that I have a point P, or say the point B for your sake. What is the value of the electric potential here? I can find it out by this. I want the value of VB. VA must be made 0. So you will move the charge now from infinity. So what is the value of VB? The value of VB is equal to work done external in moving from infinity to B divided by the charge. Can we write that now? So potential at a point, electric potential at a point B is said to be the external work done in moving a charge from infinity to B per unit. Therefore, here in books they will use unit positive charge. Sometimes they say unit positive. It doesn't matter to me. Means you can take Q as 1 coulomb also. You can take 1 coulomb. Because, see, try to understand. Initially, to make the whole scenario nice, we kept a test charge, not a source charge. Now we are saying that consider a space where there is an electric field, a uniform electric field, due to some charge which you have not seen. Our job is what happens in this scenario when some intruder comes inside. Who is the intruder? The intruder is a test charge, which is a very, very small test charge, very small test charge. And now further going, we say that the condition of study is same. Why are you being so considerate in bringing a very small test charge? Because now we have not seen our source charge. Let us bring 1 coulomb. How much you will bring? 1 coulomb. Because end of the day, you are dividing it by that 1 coulomb. So he brings a Superman, you bring a grasshopper, it doesn't matter. You're going to divide it. And that will tell me what is the potential at that point. So, end of the day, 3 things we have studied. Delta U, which is known as, tell me, can you tell me what was delta U? I don't want formulas. What is delta U? Delta U is difference in electric potential energy. Delta U is potential energy, but we are studying what? Electrical system. If it was the spring system, it is the elastic potential energy. If it was the earth and the man being pulled up, it was the gravitational potential energy. Here we are studying electric potential energy. So this delta U tells me what is the electric potential energy difference between 2 points. Then you studied something which was U. Whenever you say U, you have to give a point B. This is the electric potential energy at a point. After this, these were all where you had to be very careful. You had to bring only a Q. And this Q had to be greater than 0, very small, slow. Right? I now move to a third concept where I need to understand what is the potential difference. Not energy. Energy divided by the charge is the potential. Gravitational potential energy. So energy, because the potential of the earth is always same, whether you came and landed on it or Hulk came and landed on it, the potential of the earth is same. But the potential energy of the system changes when you came or Hulk came. Because when Hulk falls, something will get splashed. The energy is more. So at that time, so now we are trying to see what is the electric potential energy of the earth. When we see the electric potential energy, the third is the study of, delta V. Yes, very good. The third is the study of delta V. Delta V tells me about electric potential difference. This is electric PE difference. This is electric PE at a point. This is electric potential difference. Here it will be always, the word will be points. And this is very simple. This is whatever delta U you calculated divided by Q. Whatever was the external work done divided by Q. And this external point here, you could have been any point A and B. Right? So this one was W external between A and B. This one is W external specific from infinity to B. Right? Then it gives you UB. UB minus U infinity is equal to UB minus 0 UB. This is equal to UB minus UA. बोलो बच्चा, समझ में आ रहा है कभी? No issues. Here you are trying to find out the potential difference between 2 points. This is given as final potential minus initial potential. Children, whether it is electric potential or gravitational potential, this is higher potential, this is lower potential. Water will always flow from higher to lower. Bacha will fall from higher to lower. Charge will always move from higher potential to lower potential. Therefore, one very common question you used to get in grade 10. This is a 5-volt battery with 5 volt and 0. The charge will always flow from higher to lower. That's why the positive side of a battery or a cell is always shown bigger. Bigger means it is having more potential. This is less. This is the plug point of your house, and this is your TV. The plug point has a higher potential of 220 volts. The TV is at 0 volt. Therefore, when you connect and you switch on, charge will move from here to here, and flow of charge is called electricity. So the current moves from to the TV. Simple concept. Is this clear now? So this is V. And the fourth thing that we wanted to understand is what is V at a point B. So this is known as electric potential at a point. There's no difference. So this will be the work external from infinity to B divided by the charge. And here we are not very interested whether the charge is test charge means small or not. It can be 1 coulomb also. So we say unit positive charge. So this becomes VB minus V infinity divided by Q, which is VB by Q, which is equal to, sorry, not VB by Q, sorry, UB, which is UB minus U infinity by Q, which is equal to UB by Q, which is equal to UB by Q minus 0 by Q, which is equal to U. When you strip out the charge from the potential energy, you get the potential, right? So shall we quickly derive the electric potential at a point? Quick derivation, very easy, very easy. It will take just 1 minute. So let's take that 1 minute derivation out here. Very easy. You have understood everything. Just a little bit of integration, which I will explain you. You need not bother. So I have a charge out here. I have a charge out here. I have a test charge out here, right? And I have a measurement from here to here. I have a small measurement from say here to here. And this measurement is say R. So let's quickly put our values. This is Q. This is Q, right? And this distance is R, and you are trying to move, Q through a small distance, dr. I'm trying to move it through a small distance. How much? Dr. A dr distance. I'm trying to move it on this side. Okay? Understood? So let's see. We're trying to find out what is the electric potential at a point at a distance R from a source charge Q. Electric potential due to a source charge Q at a point R distance away from it. At a distance R distance away from it. Okay? Okay. So what is the external work done? Let us see what is the external work done at source charge Q. So the small work, external work done will be equal to the electric force, okay, or the electric force multiplied by dr. Rather, I should write it as electric force into dr. But when you are taking the electric force, the work becomes negative. Right? Because electric force is on this side. Agreed? Bacha? So, dW external work is how much? The dW external work is Q F electric. What is the value of F electric? The value of F electric is given by negative QE dot dr. Is this understood? Okay. Negative Q, and what is the value of E? E's value is KQ upon R square into dr. Right? Now I'm just worried about the dW external. I've taken away the vector part. Is this understood? If you want to find out what is the external work done, then you have to integrate this small d external, and you will integrate, and you want to find out the external work done. What do you want to find out? You want to find out what is the potential, at a distance r. Let's say this point is p, this point is p. You want to find out the potential at p. The potential at point p is given by the external work done per unit charge which you are trying to move. So the charge has come this side. Okay, charge has come this side. So and this will be dw external. So this will be q of this, and you will integrate it from where? You will integrate it from infinity to r, because you are trying to move it from where? From infinity to that point. This is the source charge, children. We are not moving between these 2 points. We are moving between these 2 points. Please remember, infinity to r. Is this acceptable by heart? Okay, very good. So let's do this. This will be integrating it from infinity to r, and it becomes, the q has come out. So I'm taking the k also outside. I'm taking the q also outside, right? And I'm taking the negative sign also outside, which was there. So it has a negative kq. Then don't you think it becomes, no, let me, r squared. Yeah, fine. We can keep it. kq, and it becomes dr by r square. dr by r square. Okay? Understood? So finally, Vp becomes equals to negative kq integral infinity to r dr by r square. Is this much understood? Okay, now some integration that you should know. Integration of x to the power n dx is given by x to the power n plus 1 divided by n plus 1. And you also have a constant of integration. But if it is a definite integral where you are putting this, then this constant of integration goes away, and we will put 2 upper bound and lower bound, infinity and r. That is how we will do it. We put that the c is no more there. We get a upper bound, lower bound. So we integrate this. So if you integrate this, I'm doing the integration portion in yellow so that it becomes clear for you. It is integrating from infinity to r to the power minus square dr. Okay, bacha? Okay. Can I write this as negative kq r to the power minus 2? It becomes r to the power minus 2 plus 1 divided by minus 2 plus 1. But within the intervals of this. Clear? Which becomes negative kq, right? R to the power minus 2 plus 1 is how much, beta? Minus 1. R to the power minus 1 divided by minus 1. Infinity to r. Is this much clear? Right? Proceeding further here, Vp is now equal to, now see, this negative 1 can come outside. So negative kq, then I am multiplying it with the negative 1, and inside I am bringing 1 by r, and I am making it infinity, and I am making it r. Allowed? No issues? So this becomes kq. Now how do you release the limits? The limits are always upper limit minus lower limit instead of the variable. 1 upon r minus 1 upon infinity. It is 1 upon r, right? Instead of 1 upon r, you write 1 upon capital R, 1 upon infinity. I'm changing the color of the pen now. So the potential at a point is k. K is what, beta? Q by 4 pi epsilon naught. 1 upon r is infinity, right? This is the value of electric potential at a point. Remember, in electric potential is a scalar quantity. So you will use the sign. It will be negative potential if Q is negative, positive potential if Q is positive. I would suggest now, after seeing this video, please read your NCERT textbook till the portion electric potential due to a dipole. Our next discussion will be electric potential due to a dipole. Once you understand this concept, everything will be clear to you. Clear? Things have become fallen in place now. Is this done in your school? Yes. Is it clear now? Okay, fine. So we'll stop the recording here. Our next class will be due to dipole. But before understanding any